This chapter is about molecular kinetic theory of gases, okay? And I'm going to skip on introductory slides if you don't mind, like they don't mean a thing. So first we need to figure out, what differentiates gases at the molecular level of, other states of the matter, and how we can use laws of physics to explain how gases behave at different temperatures, pressures, and volumes. So basically, three parameters that we're going to focus on are pressure, volume, temperature. Well, technically amount, but we'll get there. So the idea here is that we represent the gas as a bunch of small particles, okay? I'm going to highlight the most important keywords, that move fast and straight lines, okay? It doesn't mean that they can turn, but the only reason they can change the direction is if they are hit by another particle. Am I making sense so far? Okay. The presumption that we have within that theory is that they do not interact. Well, yeah. They do not interact except the collisions. Clear? Okay, they can hit each other, but they are not in any way repelled or attracted by any other forces. Okay? They are very far, which means they can, and this is important, they are really indeed very far. I'll get back to this. I want to consider these two bullet points together. So you see that statement, very small volumes compared to the volume of the container. So imagine this is the container, and there are two molecules. That's the ideal gas. Molecular kinetic theory can explain their behavior. Imagine the same container, but now it is super dense. It is still a gas, don't get me wrong, okay? But when we start putting those molecules really close to each other, molecular kinetic theory fails. Am I making sense? So gases in a very small volume under really high pressure, a lot of gas in a small volume, will not follow these rules. Will start like deviating from them. Okay? That makes sense. And last but not least, the energy of movement of these molecules increase when the temperature increases. So they fly faster. So 4 parameters that I mentioned before, okay, pressure, volume, temperature, amount. I'm going to start with the bottom one, the amount. I don't think there is any need in me explaining to you what amount is. How many molecules? Remember, we're mostly going to be focusing on moles, okay? For all calculations that we're going to be using, it's going to be all about moles, not grams. It's chemistry, okay? Always moles. Then, well, temperature. We do use Celsius, but in our calculations, if you see a formula, I'm going to actually put it down. So temperature, that's Kelvin, right? If we use that formula to calculate anything, it's got to be Kelvin, not Celsius, ever. Moles. Okay? Good? Now, volume, usually liters. Can also be meters cubed. There are ways. And finally, pressure, I'm not going to regurgitate what you already got. Okay? there can be different units. What is R? It is a universal gas constant. Here's the deal, folks. You should ask me right now, what if I decide to use atmospheres for pressure, liters for volume, and somebody else decides to use torr for pressure and milliliters or cubic meters for volume? Will the numerical value of universal gas constant change? The answer is absolutely yes. You do not need to remember any of those values. I promise that. Okay? Just understand that it really depends on the units people use in their calculation specifically. Okay? Clear? Now, do you need any help with understanding of the concept of volume? I don't think so. Right? Volume is just volume. What I want to focus on is this: the pressure. I want you to start thinking about the pressure at the molecular level. When a single molecule hits a wall of the container, it exerts a very, very small force, very small pressure against that part of the wall of the container. Do you agree with that statement? Yes? All good? Okay. If the more molecules you have, how would it change the frequency at which they hit the container? Do you understand my question? If you put more gas in the container, will the molecules hit the walls more or less? Dude, put more. Have you ever been in a mosh pit? The more people in the mosh pit, the scarier it is. Okay, you're going to get hit much more often. Okay, so the point is, more molecules, more frequent collisions, greater pressure. Does that make sense? If you increase the temperature, how does it affect the velocity of each individual molecule? It becomes faster, right? So the faster collision will also increase the pressure. So think about this. If you increase temperature, it should probably increase pressure. And if you increase the amount, it will also probably increase pressure. Okay? Does that make sense? Now, volume. Well, same as the volume of the container. Does that make sense? Okay. Measure it in liters, milliliters. This. What does that mean? It means that at pressure being constant, greater temperature leads to the greater volume. Okay? If you have like a balloon, put it in the fridge. It's going to shrink. Okay? Because you decrease the temperature. So this is what we've discussed already, temperature. If the temperature of the gas goes down, fewer collisions, and I'm going to add at lower velocity. Okay? If the temperature increases, more collisions, at greater velocity. Okay? Cool. Now, pressure, it's a physical parameter that one of the most hated by me because of the shit show with the units. Okay? I was taught in pascals, which is a very easy, it's a pressure of 1 Newton per 1 square meter. Then we have millimeters of mercury. Okay? the pressure that is equivalent to the pressure exerted by a certain height of a mercury tube, okay? Same as torr. Millimeters of mercury and torr are numerically the same. 1 torr is 1 millimeter of mercury. Clear? Well, kilopascals, psi, pounds per square inch, I was completely taken caught off guard when we moved to States and I realized that I don't have my beloved pascals, okay, because of the psi. Okay, right now we are experiencing the pressure from the atmosphere because it has a certain thickness, and all the gas molecules that fly around us, they hit our body, okay, that's the pressure. If you go up, in the atmosphere and it becomes less and less dense, what do you think is happening to the pressure? Does it increase or decrease? Does it climb up the mountain? Decreases, yes. Go on. No, that's the opposite. The ocean pressure, the deeper you go, the greater the thickness of the water that pressures on you. Does that make sense? So you're talking about water pressure. It's the pressure of that layer of water above you. Okay? That makes sense? This is why airplanes are pressurized. Because at the elevation, the cruising elevation, the pressure is super low. Okay? So the device that we use to measure pressure is called a barometer. Baro. Probably Latin. I don't know. Okay. So we use it as a pressure meter. Okay. Now, this. Okay. So imagine we have a tube, like a test tube, all right? Good? And we have a dish with a mercury, okay? So we flip the tube upside down, stick it in the mercury, just on the table. Do you think the mercury will go up? So what I'm saying, we have that little dish, we have the mercury, and I put the tube like this. Will the red mercury go up? No. You can try it at home. If you have like a bathtub full of water, any large container, you can take a cup, flip it upside down, and relatively quickly and absolutely horizontally put it down. The air within the cup will prevent water from going into it. Okay? The diving bell, are you familiar with the concept? The diving bell employs that concept. Now, the mercury doesn't go up because there's air in our tube, right? Now we suck the air out and form vacuum. Nothing resists mercury, and because of atmospheric pressure, the mercury will start shooting up. Agreed? Do you agree that this mercury column by itself exerts a certain pressure at the bottom, right here? Right? What Kayla was saying, but you were saying this about water, okay? The deeper you go, the greater the pressure. But we can say the same about mercury. And at the point, height-wise, at some point, it's going to stop. It's going to stop when the pressure of that column of mercury, I'm going to put like pressure of mercury, is the same as the atmospheric pressure that pushes it up in the first place. Okay? So this is how we derived those weird-ass units, millimeters of mercury. Am I making sense? So, to give an idea, what we're talking about. Air at the sea level produces the same amount of pressure as the layer of mercury that is 760 millimeters thick. It's 76 centimeters, and it's kind of like a regular arm length, give or take. Okay, does that make sense? This is equivalent to 1 atmosphere, because atmospheric pressure, or 760 torr. Okay, does that make sense? We already mentioned that atmospheric pressure is the pressure of the atmosphere from the top to the surface. Clear? Now think about this. Let's say the top of the atmosphere, 20 kilometers, right? So from me here in Ohio, give or take, we're actually a little elevated. From me to that end of the atmosphere is 20 kilometers. Now I go to Denver, start hiking in a forest. It's 2 kilometers up. So now the distance between me and the top of atmosphere, not 20, but 18. Okay? Making sense? As I go up, that difference becomes less and less, and the column of air that pushes down on you becomes shorter and shorter, and the pressure goes down. Okay? I think Ohio is like 200 meters at the sea level or something, above the sea level or something. Like, we're pretty low. Okay? So those are conversion factors. As I mentioned before, I promised to provide you with the conversion factors between different units, because it is unreasonable to expect you to know how they convert. The only thing that I really ask you, this. Okay? 760 is atmospheric pressure. It's really useful. Okay? So, remember what happens to the velocity and the frequency of collisions when we increase the temperature. What? When we increase the temperature, the frequency and the velocity of collisions go up. I cannot see your finger behind Aubrey. Okay, go up, right? Am I making sense? If frequency goes up and the velocity goes up, the pressure goes up. So the hotter it is, the greater the pressure. Changes are small, seriously. It's not like you go from 760 to 1500, okay? Does that make sense? And when it's cooler, the pressure goes down. Now, to fully clarify, this is an example of chemists going into meteorology. Air on Earth atmosphere, in its entirety, the entire Earth, is it the same everywhere, or are there differences? Of course there are differences, right? General idea how to know low versus high pressure. And I took the geography class like in high school. I can't remember shit. Why? But if it's sunny and beautiful and no clouds in the sky, atmospheric pressure is higher. Okay? When you have a rain coming in, it drops. Rain or snow, doesn't matter. Okay? Makes sense? Like, if you want to know, like, oh, okay, it's going to be a sunny day tomorrow, the pressure is going to go up a little bit. Okay. This is just, stuff. Mount Whitney, I forgot where it is. I don't remember. Okay. Where's Alexa when we need it? Somewhere in Everest. So just to give an idea, it's a little bit, it's almost 8.9 kilometers. There is a handful of there's a handful of people who actually reached the summit by themselves. Now you can buy, like you can pay, it's like 50 grand, and you will be walked to the summit and back. There's a pretty good chance not to make it, but most people do make it, okay? But there are some people who actually went from the last base camp to the summit and back alone. It's a crazy thing to do, okay? So 475 millimeters of mercury expressed in atmospheres. Okay, hear me out. You don't need a calculator for this. $760 is 1 atmosphere, right? 475, is it less than 760? Yeah. That's the only, you can calculate it, or you can just kind of wing it on a common sense, okay? This, same idea. If 1 atmosphere is 760, just going to use millimeters, okay? Then 2 atmospheres is twice that number. Everybody agrees? So 1520. That's the answer. Clear? Okay, remember that mercury barometer that we talked about before? Right? So that's our mercury, okay? The pressure that mercury exerts and the pressure that atmosphere exerts, how do they relate? Huh? You can say it. I'm not going to make fun of anyone. What do you think? No. What I'm saying is, like, there's a pressure exerted by atmosphere, right? There's pressure exerted by mercury. The top is steady, doesn't move anywhere. So what do you think? What's the relationship? Yep. Yes, but like if you will increase atmospheric pressure and it will become greater, the mercury will move up. If you decrease atmospheric pressure, the mercury will move down. All right? Everybody? Okay. So you can make the same barometer, same type of barometer, using water. Okay? But you will have to make it 13.6 times taller. So basically not 75 meters, but something like closer to 10 meters tall, like 3-story building. Why? Oh, come on. Read the answer. Huh? Yes, of course. Water is less dense. So if you would, hypothetically, it's not, okay, first of all, if I would throw in the sea of mercury, you're not going to sink because you're not dense enough. That makes sense? But if hypothetically, somehow, I would be able to drown you in mercury, if you would go at, say, like 2 meters deep in mercury, it would mean 27 meters deep in water because mercury is so much denser. Clear? Good? Okay. So I'm going to, well, actually, I'm not going to illustrate anything. We're going to stop right here because these laws, it's a bit of a math then. Okay, so we're going to put it on Wednesday.